Hello, so continuing on this click on test 16, the last problem, which is 1301 number of paths with maximum square. So the problem says we get a square board of characters where we can move on the board by starting from the bottom right at the character S, and then we want to reach the top left square, which is marked with the character E. And the other squares that are not like the top right, the top left, and the bottom right contain numeric characters 1 to 9, or they may contain an obstacle X, right? And for each move, we can move either up on the board, or a left, or we can move up left diagonally. And we can move there only if there is no obstacle, which is the character X. And the goal here is to return the list of two integers, such that the first integer represents the maximum characters we can collect while going from start to end, and the second number represents the number of those paths that contain the maximum, that give us the maximum number of characters we can collect. And the count, we need to return it modulo 10 to the power of 9 plus 7. And if we can't find any path, we need to return 0, 0. And so the board looks like this, may looks like this, and then for this example, if we look at it, let's say the first example is like this. So you could see here we could get we could go left, so we could do 2 and then go left again, do 1, so 3, and then go up, get 7, so that would be 3 and then 2, so 5. So we could reach with 5, but we could also go up 2 and then go up 3, so that's 5, and then go left, that's 7. So this one here is a better solution, and there is only one way to get it, so we return 7 and 1. So that's the first example here. And the board is a square because both the number of rows is equal to the number of columns, and it can be at most 100. So let's see how we can solve this problem. Okay, so let's see how we can solve this problem. So the problem first asks us for a pair, right? So we want a pair of the maximum sum we can collect, right, from start to end, and then number of those paths, or the count of those paths. So that's what the problem asks, right? And so maximum sum here and enumerating the number of paths, we can directly think about using dynamic programming. It suits very well these cases because there is no way for us to know in advance without trying everything and seeing which solution is better. So that's what we'll be trying here. And so, well, if we are doing dynamic programming, we have two possibilities. We can either start with the top-down approach or try to do a bottom-up one. I think it's easier to think about and understand a top-down approach, so let's start with that. So the first thing we need to determine is what is the state, what is the state we are concerned with here. So because with the top-down solution, we will need to recurse, right, on some state, and so we need to figure that state out first. So what is that state? So according to the problem, we know that we have well, there is the position, right, the current position. That's what matters the most, right? Let's call it IJ, because from there we can go left, up, and up left, right? Or up left diagonally. So that's the only thing actually that we need. But the state here we need to return the pair that we are interested in, which is current max sum and current count of paths, right? So those are what our recursive function needs to return, right? And the other thing that we need to think about is, well, what is our base case? Well, we know that there are two special cases that we need to handle. One is the start position and the other one is the end position, right? So for the start position, for the end position, so if the board at position ij is equal to E, the end, then we are done, right? So we need to just return, well, there is no sum to collect there, so 0, and there is no, so the count when you reach the end, there is one way to, you already, so from a cell you reach the end, right? This is one way, right? So we need to return 1. The other base case is when we are starting, so when we are at the start position. And for that case, well, we have 0 sum and 0 path yet, because we don't know, we haven't reached the end yet, so we need to return 0, 0. So we know our base cases. Now let's think about how we can find the recurrence or the choices that we have at each point. So the choices, what are the choices that we have at each point? And the point here is ij, right? So the problem says, well, we have 3 choices, right? We can go left, right? And we can go up, and then we can go left up, or up left diagonally, basically. Sorry, I forgot here another thing actually. Sorry, here I meant x when there is an obstacle. So when there is an obstacle, we can't move anywhere. So the sum is 0. We can't collect anything, and the paths is 0, because from that obstacle we can't reach the end. Now these are the choices that we have, so we need to just handle them, right? So what do? We call the function. So let's just call our function here with the that we will recurse on. Let's call it helper for ij. So going left, what does going left mean? So going left means calling basically helper at i-1 and j. And of course we'll need to check the boundaries, we'll need to check that it's not an obstacle, right? And then so basically before each, so for each we will need to check in bounds, and that's not like less than 0 or more than the length of the board, and different than an obstacle, right? And then what does go up mean? So go up means just calling helper I and going up, so j-1, right? And what does go up left mean? So that means just calling helper on i-1 and j-1. So we know how we can recurse, but we will need to somehow keep the sum here. So for each of these, right, we can store it in a variable, right? So what we will do is we will of course check that it's valid and everything, and let's say for example for the go left case, we will call it s1 and count 1. So this is the sum that we get when we go left, and the count is what the number of paths that give us that sum, right? And so this would be helper of i-1 and j. And so we will, if the count 1 is more than 0, because if it's 0, that means maybe we encountered an obstacle, right? And so we shouldn't use the sum. But if it's bigger than 0, that means let's add to the sum the value of the current cell, right? Which is basically converting the number at board ij to an int and adding it to the sum, right? Notice that here if it was x, we would have returned 0, right? And we will do this exact same thing for going up. So going up, we'll do a similar thing here. So we would have s2 and count 2, which would be equal to the values of going up. And we'll do a similar thing. If count 2 is bigger than 0, then we will add to the sum the value of board ij. And again, we'll do a similar thing for going up left. And so that would be also if s3, let's call it, and count 3 a helper at I minus 1, j minus 1, and if count 3, which means there is a way to get there, we will add to S3 the value at board ij. Okay, now we have the result of all choices. Now how do we choose the best choice? So we have a couple of cases, right, that we need to handle. So case 1 is if all sums are equal, then we will need to add up the counts for all of them, right? And the sum is just the same. So the count counts how many paths to give us that maximum sum. If the maximum sum is the same for all of them, that means we need to count all 3 ways, right? Because that's what the problem asks. If only S1 and S2 are equal, then we will need to add up count 1 and count 2. If, for example, only S2 and S3 are equal, then we will add up count 2 and count 3. If none of them are equal, then we will take the one with the max sum and return the sum and the count, right? So if all of them are equal, then the result as the final ascent count would be what? Would be S1 or whatever, because they are all equal, and then the count of all of them. Count 1 plus count 2 plus count 3. Now if the second case is if so the second case here is if only, let's say, S1 is equal to S2. At that point, well, S count would be the S1, right? And count 1 plus count 2. So this is, of course, else. The other case would be if S2 is equal to S3, then that means S and count is equal to, of course, S2 and the count of 2 plus the count of 3. That's the sum of the ways we can get this maximum sum. Now otherwise, the last case, none of them is equal to the other, which is here just the else. Then we need to return the max of all of them. So let's say we want the max of S1 count. Sorry, I forgot here. It's actually, so here it's this, right? But here maybe S3 is bigger than S1 and S2 both, right? So that means here we will need to get actually the max. So we'll need to get the max of this pair S1 and count 1 plus count 2. And in case S3 is bigger than both, then we will need to return that. So this max here with Python, it will get us either one depending on whether S1 is bigger or S3 is bigger. And if both are equal, which is not the case because we already handled it here, right? Otherwise, here we will need to also get the max. So here we'll need to get the max of S2 with count 2 plus count 3, or maybe S1 is bigger, so let's pass also S1. Otherwise, get us the max of all of them, right? So S2 count 2 and S3 count 3. So now we will have, so here get the best of all choices. That's what we are doing here. And once we are done, we can just return S and count. There is just one thing we should not forget. The problem asks us to return the count mod 10 to the power of 9 plus 7. So this is just following the problem statement. But this is pretty much all there is to it, right? We just do the base case, recurse on all the possible choices, take the best one, and return it. So this recurrence here, of course, will have some repeated calls, because maybe the one when we go left, we can go to it by another way, so we shouldn't recompute going from that point to the end, and so we'll need to do some memoization, but essentially this is the solution. So right now what I will do is I will write this in a more clear way on Leetcode and then apply memoization, right? But essentially this is the thought process. It's what is our state, what are our base cases, what are the choices that we have at each point, and how can we determine the best one. And that's pretty much the template here that we applied. Yeah, so let's write this and see if it passes. Okay, so now let's write the solution here that we just went through. So the first thing we need to do is we need to define our helper function here, right? So the state is the current position that we are at, and we do the base cases, which is checking if this is equal to the end. Then we need to return 0 as the sum because there is no number to collect there, and we reach at the end, so there is one way to reach the end. If we reach an obstacle instead, so if this is equal to x, then we need to return, there is nothing to collect there, and there is 0 way to get to the end because we can't move from x, right? Now the other thing is, let's initialize the variables that we need. So we need s1, s3, count 1 for each choice, right? So each choice here, we'll initialize the variables for all of them. And after that we need to do the first choice, which is choice 1 here, go left, and choice 2, go up, choice 3, go up left. Okay, so choice 1, we will need to check if the current cell is, if going left, if the cell on the left is valid, right? If it is, so I will need to define is valid here. So is valid for a position just means that, it's in the boundaries. So let's just define a function called inbounds. Which just checks that it's in the range 0. Both I and j are in the correct range. So length of board, so this is I. And G is in, since it's a square, board is equal to board of I, so this should be enough. And here we just return if it's inbounds, and it's not an obstacle, right? And board I j is different than x. And so if it's valid, so here for the left one, if it's valid, then we get the sum that we can get and the count that we can get from going there. So going there would be I minus 1 j, and we check if we can get at least one path going there. If it is, then we add that to the current value. So let's just call a function here, get, that gets at the value at the current position, and let's define that. So to get the value at the current board, we need to return. So it's an integer, but as you see here, in the example, it's in a string, so we'll get it as a character, so we need to convert it to an int. So int of board ij. And we just need to be careful in case it's the start position, right? So this is if, let's call this maybe C. If it's not the start, otherwise, if it's start, then return 0, right? Because that means we don't want to add anything. And then go up, which means it's just I and j minus 1. So we'll do a similar thing here, except it would be S2. and we'll call the next function for j minus 1 to go up basically, and if count 2 is bigger than 0, we add the value for s2. Do similar thing for go up left, which here would be I minus 1, j minus 1. So it's s3 and count for 3, and then after that we will take the best of all choices. So take the best choice among all these 3 choices, right? So we will handle all our cases. So the first case was all of them are equal, and at that point we just say s and count are equal to the s1 and then the count of all of them, right? There are all these ways to get to the maximum sum. Or the second case that we said, which is s1 equal to s2, and at that point our s and our count are s1 and the count is just the sum of all these 2. Or maybe it's better to just go maybe it's better to just do maybe s3 is better than s1 that is equal to s2. So we will need to take the sum of these like this. We'll need to take, sorry, the max of them. So the max of s1 and s3. Otherwise, maybe s2 is equal to s3. I know this is cumbersome, but we are just enumerating all cases, so it's pretty straightforward. So if it's s2 and s3 that are equal, well, it's either the max of these s2 or s1, right? So if it's s2, then we need to count both s2 and count 1 and count 2 and count 3, because those 2 are equal. So we need to count all these ways to reach the max sum. Or maybe it's s1, right? So we need to pass that like this. Otherwise, they are all different, so we will just pick whichever one is best. So that would be taking s1 count 1, s2 count 2, and s3 count 3. Okay, so now that we have this, we can just return s and count. We'll just need to define here mod, as the problem says, which is 10 to the power of 9 plus 7, and we will need to mod count here with, we need to do count mod. That's what the problem asks us to do. And we'll return by calling helper on what? On the start position, which is at the bottom right corner. So it's at length of board minus 1 and length of board minus 1. And that's pretty much all. Let's just make sure our indentation here is correct, which it isn't. So okay, so this should be it. Let's just make sure. So this is good. S1 count 1 plus count 2, S3 count 3, S2, S1 count 1, and yep, sounds good. Let's run this. Okay, so there is an error somewhere. So this is correct, checking that we are in the right bounds and that it's not x. If it's the end, 0 and 1. If it's x, 0, 0. Initialize all of them. Check if it's valid. So we will go left here, I minus 1j. If it's bigger than 0, we get ij, which is just, yeah, I forgot here to pass int c. So it was returning 0 all the time. Yeah, sorry about that. Okay, so that passes. However, if I submit this right now, I will get time limited exception because there are some cases with these helper calls that I will call multiple times and recompute multiple times. And so to not do that, let's just have this caching map here that we will add. So for the position ij, we will cache the result and return it. And then next time that same call happens, we'll just return the cached result. So that would mean here, before calculating and recursing on the substate, we'll check first if ij is already cached. So if it's cached, that means it's in memo, we can just return that. Okay, so now we can submit the solution. Okay, so that passes. And so with this solution here, we know that a helper would be called at most the length of the board, right? The number, so the length of the board. So if length of the board, so if the board is n by n, this would be called n squared times. And so time complexity, that's n squared. Same thing for the space complexity because of both the stack and the memory 2D here, the memory map that we are using here. Yeah, so that's all for this problem. Thanks for watching and see you next time. Bye.